whenever it is needed to solve the problem and return the results back to FEAMAP for post-processing. So our interface is with FEAMAP. FEAMAP takes care of, calls Nastran for solution and gets the result back. So we work with FEAMAP, and this is the environment that you see FEAMAP. Before continuing, I want you to not just try to click what the commands that I tell you, but explore the program and have fun with this program. This is a user-friendly program. Previously, it was much more difficult. We had to write a program, actually. We have to write the script of the program. But nowadays, it's much simpler, and these are all like windows open up, and then you select, make selection. So have fun with this and explore more than what just these clicks that I tell you. So the program is very capable, and you learn very powerful tools here. So with this now, let me, first of all, in order to learn a program, the best way is to look at examples. Where do you find examples? Go to help. Okay, it takes a little bit time to open it. Go to help examples. You see examples here. I clicked on this, but it's not showing.
Sorry, I have two screens open and it popped up on another screen. Let me pull it over for you.
Okay, yeah, excellent. Very good. Thank you. This is the examples that you have. So this, a lot of examples here. You see this list here. You can always go back, look at how a problem, for example, if it is a static analysis, if it is an assembly, it's a buckling problem. If it is, what else do we have? Geometry, meshing. If you have, for example, a beam problem, so click on beam problem. This is analyzing a beam model. So it goes through steps of how to create this one, how to make the mesh, define the beam property, and so on and so forth, how to meshing the model, and then it goes into all the steps that you need to analyze this. Analyzing an axisymmetric model, analyzing a mid-surface model. It's like a plate or shell you decide on the, this is a mid-surface model. You can do heat transfer problems. You can do vibration problems. Look at this one. It is a direct transfer. This is the modal frequency. So this is a vibration analysis problem. If you are doing heat transfer problem, steady state thermal heat transfer problem. So this is a heat transfer. And if it is, for example, plastic deformation, these are large deformation problems. These are nonlinear problems. Yes, this it says here, nonlinear material properties. So these are large deformation, multi-step structural analysis, and surface-to-surface contact stress problem. So these examples you can always consult when you need to do this. So keep, just have in mind that these examples are very good tools for you to learn a new problem. With this now, I'm ready to go over solving a two-dimensional truss problem, a simple truss problem. I'm going to create this one. Always, whenever you have a question, feel free to discuss also. I'm going to create the geometry first, and then define the material properties, define the model properties, then define the material itself, then define the constraints, boundary conditions, loading applied, and then run this. So these are the steps that I'm going to do. Let's first create the geometry. I need to create the, yes.
Would you mind if we recorded this lecture? I know you don't want to record all of them, but would you mind recording this one?
Sure, that's fine. Can you do that? Or, I mean, because I don't have the screen.
Let me see.
You can control Tyler's screen. I can control it, but...
it says I have to ask you to give permission to record.
Zoom. Meeting controls, hype. I don't know where
it's okay.
I mean, view. Oh, that's view options. I don't know.
Sorry, it's not a big deal. I thought this one would be helpful to have.
All the steps are in very detail. Actually, the handout that we have for this week, it tells you all the details actually, and more than what actually I will go through. But I don't see.
All right, that's fine.
Hide video panel. Okay, well, it is record here. Yes, record on this computer, record to the cloud, record on this computer. Okay, I click on record. All right, I think it is recording now. Let's go through this simple two-dimensional truss problem. I'm going to create the node first. I need to first create the geometry. And to do this, you go to model. I'm clicking on model, and then you go down to node here. I have to define the nodes. It goes under this. So ID 1, this is node 1. Coordinates are X, Y, Z. They are already 0. So I want to put the coordinate system at node 1 with coordinates X, Y, Z, 0. So that's fine. Say OK to this one. It automatically. The problem is it goes under these windows, but that's all right. I pull them back up, but you don't need to do this. It would be at the right place in your on your computer. For node 2, it is ID 2. I want X to be 100, and I want its Y to be also 100. And Z is 0. It is just a two-dimensional problem. Say OK to this. It goes down here. I have to pull it back up. The X put for the next one. This is ID 3. Node 3, it would be 3. And it's for node 3, I'm sorry, X is 200. Its Y is 0. And Z is 0, say OK to this. And for node 3, there is for node 4, I don't have anything. So cancel to finish this process. On your screen, you see actually these dots which I created. I see one of them here. Let me see what I created. So I'm pressing the Control and the left mouse button to drag it down here. You see actually 3 nodes, 1, this, and this. A very light color is difficult to identify them. So let's have the node numbers written. I want to show the node numbers, make sure I have done it correctly. So go to View. You can go to Options. Then here, this labels entities and color. It is radio button is checked already. Click on node here and ID. I want the ID of this to show on the screen. This draw entity checkbox is already checked. Say apply to this, and you see this node 1, 2, and 3. Say OK to this one. So these nodes are created now. Now I want to define the material. Material is, I have the modulus of elasticity. So I need to go to Model, Material. And here for modulus of elasticity, I need to enter 1, enter exponent. This is 6. So it is 1 times 10 to the power 6. You enter it like this. It is PSI. You don't need to specify the units here. As far as you are consistent with the units, you are fine. You don't need to specify the units when you do static analysis. In vibration problems, we need to specify the units, but FEAMAP doesn't require this, because as far as you are consistent, just stay with pound, inch. So stresses will be, let's say, in pound per inch squared, and so on and so forth. So,
Professor?
Yes.
Sorry, I missed it. What do you click to get here?
Model, material, and that is this window.
Okay, thank you.
Sure, modulus of elasticity, you enter it here, and then say OK to this. It goes to ID 2 for the second material, if there is another material. I don't have any other material. I want to finish this process. I cancel to this. So it is done. Then I need to specify the model property. Go to model, property, then click on element property, this element property type. And this is a truss problem. These are different types of elements that we can use. This is a truss problem, so we need to just click on rod here and say, okay to this. It hides this, I have to say okay to this. And then it wants to know what the cross-sectional area here. For cross-sectional area, you type, what I have is 10 inches squared, so enter 10. And finally, I need to specify what type of material it is. Press on this and select isotropic material. Say okay to this. This is for ID 1. Say okay to this. It goes for ID 2 if there is another material property. Say cancel to finish this process. So I did this part. I now need to define the elements. For elements, you go to model, element. It hides here. You don't need to pull this up. I have to do this one. It is ID 1, element 1. You can click on this. Element 1 goes from node 1 to 2. So you just click on this, it shows it here. So element 1, ID 1, goes from node 1 to 2. And for the property here, you specify that this is a rod property. So click on property and rod property here. So okay to this. This is element 1. I want to define element 2. It already is here. Just you need to bring it up. So ID 2 goes from node 2 to 3. You can click on this. You can also enter them here. This is node 2 to 3, and this is already the property is rod. Say okay to this, and it automatically goes to another one. So I don't need anything else. So okay, say cancel to this. This is the structure I have. You can move it around by pressing the control key and the left mouse button to drag this wherever you want. Next step, I need to define the, I want to also show the element number. So it is helpful to make sure that everything is correct. So you go to view, options. This radio button labels entities and color is clicked already, selected. Select element, click on this element here, ID. This draw entity is already checked, that's fine. Say apply, and then say okay. You see element number 1, 2. This is the truss that actually I am solving. Nodes 1, 2, 3, and 2 elements. Element 1 and element 2. Next step, I have to define the displacements. For displacements, I go to model, constraint. Constraint is on node, nodal constraint. I want to constraint set. You can describe it, for example, constraint set 1, set 2, whatever description title you want to give. I don't want to give any title now. Say okay to this. Then it opens this window for you. Which node do I want to define? I click on this node 1. It appears here. I want node 1 and node 3. 3 appears here. Say okay to this one. It tells you what type of constraint it is. These are pinned. You can click on pinned. It shows translation in the X, translation in the Y, and translation in the Z. These are 0. That's what I want. This is pinned. The other one is rotation about X-axis, RY, and RZ. Rotation about Y-axis, rotation about Z-axis. You can specify whatever it is. But this is a truss problem, so these are pinned. I say okay to this one. It automatically goes to another set if you want another types of nodes, but I don't have anything to say. So else. So, okay. This as what you see, 1, 2, 3, 1, 2, 3. These are the constraints. It means that it is fixed, it is pinned at these points in the X, in the Y, and in the Z direction. So that's the constraint. The next step is to define the load. I want to apply a 10 kilopounds load, pull it upward. So go to model, load. This is nodal load. Again, it asks whether you want to call it, give it a title. You can enter it, for example, load set 1, so that's fine. Say, okay, to this, I don't want to give a name for this. I click on this node 2 here. It appears here. I selected this one. You can also enter it here, ID 2. Say, okay, to this one. And it says what type of loading, create a load on this node. This is force, type of force. In the future, we are going to apply other things for stress or for distributed loading on the structure and so on and so forth. In the Y direction, I want to specify that this is a 10,000 pound load. This is upward, say okay to this. And it created this already. It goes to another one if you want to specify anything else. I don't have anything else. I want to finish this, say, cancel this. So this is the truss that we defined, the constraints and the loading and then the geometry and properties. We are ready to analyze this model. Go to File, Analyze, click on Analyze. Now it says Export Method. We want to create Edit Set. Click on Create Edit Set, Analysis Set Manager. This is a new type of analysis. Click on New. Here you can give a title to this, or it says Analysis Program. This can interface with, of course, other like MS Nastran, ANSYS, another very widely used program in the world. Abacus, very unique, very for research. Usually people use this one, very capable program, research-oriented. If there is research, of course, we go with this one. And FEAMAP structural, MSC, MARC, SimCenter. This is what actually we are using. So the program already selected this one for us. And analysis type, we can have different types of analysis. This is static analysis. If it is buckling, if it is vibration problems, if it is a heat transfer problem, you can select, for example, this one, transient heat transfer or steady state heat transfer, and so on and so forth. So it is a static analysis. This is integrated mode. We are not using it directly communicating with Nastran. We are communicating with Nastran through FEAMAP. Say next to this. A couple of other windows will open up. We don't need to make any changes actually to this. This one, executive and solution options. You don't need anything. Say okay to this. Say next to this. Another window, bulk data options. We don't need anything to this. Say next to this. I have to pull it down up all the time because it hides it under this. Cannot be given. Say okay to this. This is geometric check. Say next to this. You don't need anything here. Say next to this. You can specify master request titles next to this. This window has boundary conditions. You see that the constraint, I didn't give a name here. You can click on this. I didn't give a name, it's untitled, but you could just give a title, it would show here. You can run with different types of constraints if you want. A load, I didn't say anything, so it is untitled. Then you click next to this. Now, this one, output request, I want to specify what I need from Nastran. These are already checked displacements. nodal constraint forces. This is fine, element corner results. Now here results destination, open this one and select print and post process. It tells Nastran that solve this problem and then return the results back to FEAMAP for post processing. This one, return the result back to FEAMAP, otherwise FEAMAP will not get the results back. Say okay to this. It takes us back to this analysis set manager. We are done with this. We are ready to analyze. Click on analyze. This is running. You see this window is nothing here. Okay, it solved the problem. Finished, you see this result here. Nastran finished this problem. A couple of items here. This file F06 that you see here, everything, all the summary of the results are here actually. So it is very helpful in future to look at this file. There is a file already created. It shows it here, but also there is a file in the directory, in the folder that you created for this problem. You see a file with .f06. Double click on that file in your directory or in your folder, then it opens this file. This file gives a summary of everything actually of this analysis: nodes, displacement, stresses, forces, reaction forces, whatever you want. So pay attention to this F06. I don't need it now. I close this one. Let me just show you some of these results. I first want to show to see the deformed shape of this one. Of course, there is shortcut key. You can click here. You see this is deformed. This is the deformed shape of this structure. This is undeformed. This is deformed. And you can click on this dynamic. Actually, it shows that this was this motion is actually like this. But let's see where we can find these commands also with more options, not just with the shortcut key. You can go to view, select. Here, click on, you see deformed and contour data. Click on that. It opens this window. Select post-processing data. We have only one output set. We could run, for example, different sets, but we have just case one. Here, output vector for the deformed, it is already total translation selected. You can select other items here, but this is fine. For contour, I want to also see the contour of total translation. Say okay to this and say okay to this. Let me see, I don't see any effect. Did I do anything wrong here? Let me do it one more time. View, select. I have the, let me see here. If I view, select, and oh, okay, I had to click on this deform and contour. I'm sorry, these two I forgot. Click on deform. In the handout that I'm giving you, all of these are described: deform, contour, and this one it is here already done. So say okay to this, and so okay to this. You see this contour refers to this bar. It tells you, it gives you the results. For total translation, you see here total translation, and this is the total translation. You see the maximum, this red color here, you see 0.1414 inches, the maximum displacement, and the minimum displacement is 0 already. These points do not have any displacements. I prefer to have a graph, just move it, let's see, control and just drag it down here. I want to show the deformed and undeformed superimposed. Like this, I don't know really what it was at the beginning. This is the deformed shape. To do this, you can go to View, Options, and you select this radio button, Post-Processing. For the click on Undeformed, Draw Entity. View color, you can also change the color if you want, whatever color. You can click on this. It shows a palette, for example, if you want, let's say, to show, let's say, red, and you want with dashed lines. That's fine. Say OK to this, and say apply to this, and say OK to this. So what you see here, this is the undeformed shape, this red one. And the other one is the deformed. So it means this structure, when it was not loaded, it was like this. When it is loaded, it is like this. So it is helpful to see how this structure responded when we applied this load. It makes sense. So it is a good point to see whether our analysis makes sense or not. So that makes sense that this seems correct. Let's now do one more item. Let's see what we want to do. Sometimes we want this picture. This is very important actually from our result. Always we want deformed and undeformed shape. If you want to keep a copy of this in the report, for example, you go to File. You see here picture, where is picture here? And click on Copy. And then that's it. I have a copy now. I can go to Microsoft Word and paste it. So it gives a very clear drawing on what you see on the screen. This is your main screen here. By the way, these are some pull down menus here on top. These are shortcut keys, and these are some commands that you select from. You can select from this model info. And down here, always pay attention if FEAMAP has some messages for you, it shows it here. Sometimes FEAMAP needs your response to something. It cannot proceed without you to respond to FEAMAP's question. So keep an eye also on these messages from FEAMAP here in this window. So with this now, this is the plot of the results. I want to also do some other things. Let me show you one more thing before I let you do your work. I want to see the displacement table. I want to create a table and show these, for example, forces or stresses or displacements. To do this, you can go to List. I want to now show the displacements, numbers, and since I have the also exact solution, I want to compare to show you how it compares with the exact solution. So go to List, Output, then what did I do? List Output, I'm sorry, this is List Output, and then go to Results to Data Table, click on this one. Result to Data Table here, this is fine, say OK to this. Now it tells you what do you want. The output, it wants to create a table, it wants to know what you want. Here you see a quick filter. I select nodal. I want displacement at nodes. You can find, for example, filter and show you just what is relevant for elements. So click on node. I want these are T1 translation, T2 translation, T3 translation. T1 is translation in the X direction. T2 is translation in the Y direction. And since there is nothing in the Z direction, so let me also show, but I don't have anything. It's just a two-dimensional problem. So T1, T2, T3, I want to show. This is already checked. I only had one case. Say OK to this one. It wants to know entity selection. Where do you want? What nodes? I select all. Click on Select All. It shows all the nodes from node 1 to node 3. Say OK to this. And it should show the table here, which I don't see this. Let me see. This is the data table. Maybe it was blocked. A data table. I have to do this again. I think this was blocked, so it didn't show this. So let me do this piece one more time. You can go to list, output, results to data table, select, say OK to this. And here for the filter, you select node. And I said I want T1, T2, T3. Say OK to this. And I want to, for all the nodes, select all, say OK to this. And here is the table. Let me a little bit. Let me show this a little bit better. You can put it on a clipboard and also take it to copy to clipboard and paste it in your report, for example. Let me open this a little bit more. You see that here, ID, this is node 1, 2, 3. These are coordinates, X, Y, Z. These are coordinates of these nodes, and these are translation in the this is T1, translation in the X, translation in the Y, translation in the Z. So it means that node 1, displacement in the X, Y, and Z 0. That was fixed. This is node 1. Node 2, this is this node. Displacement in the X direction is 0. Displacement in the Y, it is 0.141421. And displacement in the Z is 0. It was not a 3D problem, so Z is 0. And node 3, X, Y, and Z displacement 0 because it was pinned here. So these are the results in a table form. We can get stresses, reaction forces, whatever we want, like what I showed you. Again, handout gives you details of all these steps that you need to take to get these items. Let me see what else I want to.
So you could put deformation of like element 1 and element 2 in that table as well?
Deformation, not for elements. Deformations are for nodes.
Oh, okay.
Displacement are for node. This node, but element, it is a continuous. At what point in this element you want the displacement? The displacement of one point is given. So these are nodal displacements. But elemental, it is stress or force in an element, but not
Right.
displacement are not for elements.
Right. Okay.
All right. Any other questions? Anything? Okay. So that was a discussion I wanted to show you about this. Remember, let me see. The displacement, we found this to be you have to drag this. Displacement, remember, 0.1414. Let me check it with the exact solution. If you don't have any questions here, I need to stop sharing this one. So we are done with this. So if you, for the share screen, this is stop, there's a screen sharing. You want to say yes. So I'm back to actually.
Want me to stop sharing?
Yes, if you could please stop that one, that would be great. Stop sharing. Now, what do you see on the screen? You see the syllabus or?
Your syllabus, yeah.
Okay,
Syllabus.
you're back to my screen. Let's go to module. You have this, we said that module 4, activity 3, we are here. Let's click on this. This is the step-by-step instructions of how you create this problem and you run it. Everything is described here. What I need from you, material to hand in for a grade. Print a plot of deformed and undeformed shape. You know how to do this. Both of them superimposed, not two graphs, just one. both superimposed so we can see whether we have done it correctly, it makes sense or not. Always find ways to verify your solution. So whether it is deformed and undeformed shape, it is a good way to see if we have done it correctly or the deformation is in a way that it doesn't make sense, for example, with respect to the load that we have applied to the structure. So deformed and undeformed shape superimposed with contour of nodal displacement. Where is the location of maximum deflection? So locate that point. Does it make sense to you? Describe in your report, print a table showing the forces and stresses in each element. The handout tells you how to get this, the same table that we get for displacement, the same. In another table, so I need two tables from you. Show the reaction forces. So in another table, show the reaction forces at support. Again, handout tells you how to, you can get this the way that I also showed you, but you do it for reaction forces. These are SPC, it is called single point constraints, SPC. Whenever you see these are reaction forces. On your plot of part 1 above, indicate element which carries the maximum stress. So you see the stress from this table and point which element carries the maximum stress. The title of your computer run should include your name, course number, title, assignment number, and date. Here in this handout, it tells you change the title of your computer run. It tells you how to, you can change the title. So in your output, you can write your name and activity number and problem number, whatever date and everything else. So you go to model info, it tells you how to do this. Click on the plus sign to open this and you click on this manage, and then you can enter your for the title, enter your name and course number and everything. Let's say okay to this. So in the output, it will show your name. That's what I want your name to be on the computer run, and in your report show this. Submit the above information in a brief memo format to myself. Now, a memo format, see next page for a sample of a memo format. This is a memo format here. You do it like this. To, that would be to me. From, that would be you. Subject, you write it as, for example, activity number 3, finite element analysis of a two-dimensional truss problem. Problem number, I don't know, 323 of our textbook. Date, you write the dates here, and the body of your report here, describe the activity and your work. First start with the problem. This was a two-dimensional truss problem, and show the drawing of the truss problem that you solved, including your report, how you created the geometry. Describe, you created the node by entering the coordinates and then the elements, and how you applied the loads, boundary conditions, and then also the results that you obtained. Included in your this memo format like this. You can do everything and limit it to 2 pages. You don't need a very large report, just limit to 2 pages, everything you can fit. I usually don't spend this much time describing these items because this is activity. I want you to be active. But for the first class, I wanted a better description and explanation of this program. So we run this two-dimensional truss problem. You are ready to do this in the future. I just spent 10-15 minutes describing each activity, and then you are ready to do the work. This is due at the end of the lab period usually, but you can, you need to submit it at the beginning of next week's lab. So at the beginning of next week's lab, just 5 minutes, I give you, Canvas will accept your report. Make it a PDF file, and then be ready at the beginning. I tell you, yes, Canvas is open to download your PDF file, and then that's it. You download your activity for this week, and then next week we will do another assignment, continue with FEAMAP and NASTRA, do a beam problem, and continue with in the following weeks with FEAMAP and NASTRA. All right, everyone, I stop here. Any questions?
Professor, I had a quick question.
Yes.
Just to confirm, the plots and the tables that we generate will all go in the area where it says describe your activity and your work within those 2 pages, right?
Yes,
Okay.
Yes, you include them here. So it tells you how to get force and plot results, deformed and undeformed shape. It describes you in detail all the commands that you need to select, get force and stresses in each element. It tells you how you can do this and get the reaction forces. It describes how you can get this, and then you save this table, for example, under that copy on clipboard, and then you go to Microsoft Word and paste it. So that table will be available and as what it is describing. Create the table. So you create this one and paste it in your report, the body of your report.
Thank you so much, Professor.
All right, sure. Any other questions?
Since you recorded this lecture, will you be posting it as well or no?
Well, if you want, I will do that, sure. I have to first locate this and then I will put it, yes, I will do that.
Thank you.
All right, sure. Any other questions?
No, everything seems clear. Thank you, Professor.
All right, sure. Everyone, I stop here. Have a good rest of the day. I will see all of you on Monday next week for our lecture. Everyone, take care. Bye.
Take care, Professor. Bye-bye.